Hi, welcome back to the course Foundations for Machine Learning. We are continuing to learn mathematical foundations for machine learning, especially linear algebra. So far, we looked at how matrices are essentially representations of linear transformations in two-dimensional or higher dimensional spaces. And we also saw how different matrices can represent rotational transformation, shearing, or even composite transformations where rotation and shear can happen at the same time. And there could be scaling up or scaling down. All of these transformations can be represented by matrices. But you must have noticed one thing, and a natural question may have come to you, which definitely happened for me when I was learning this for the first time. So we always were looking at square matrices. So in 2D space, we were mostly looking at 2 by 2 matrices. So if we had a matrix that looked like this, let's say 3, 2, 1, 4, then this is a transformation in 2D where the I vector is transformed to this position 3, 3, 1, and the j vector is transformed to this position 2, 4. So this transformation, what it does to the I vector is such that the unit vector I will go to 1, 2, 3, 1 over here. So this will be the new equivalent of I, so the new basis vector. And 2, 4 is this. So is this actually. So, oh, sorry. 2, 4 is this guy. So this will be the new basis vector equivalent for j. And now any vector in the xy plane we can represent using these new basis vectors. So this is what we saw. And if we have a matrix like this, that can be called as M, and if we have any vector v, then this creates a new transform vector, and that transform vector we can represent in terms of the new I vector, which is this I transformed. And this is not necessarily a unit vector, but it's just the transformed vector, and the new j vector this. So this is what we saw so far. Now you may have a question which is very common, is that what if this is not a square vector? In real life you don't only deal with square vectors, you deal with square matrices. You deal with matrices that are rectangular, like non-square matrices. So this lecture is about what are the transformations that can result if the matrix itself is a non-square matrix. So let me take an example of a non-square matrix. This is a 3 by 2 matrix. So you have 2 columns and 3 rows. What does this matrix do? And on what type of vectors does this matrix act? So if we go by the logic of what the columns represent, we know that the first column represents the position where the I vector lands. The second column represents the position where the j vector lands. So this is a 3 by 2 matrix. So there are 3 dimensions for the new transformed I vector. There are 3 dimensions for the new transformed j vector. So what does this mean? What this means is the I vector, which was originally in the xy 2D space, is now transformed into a 3D space, because now the new I vector has, the transformed I has 3 dimensions. It has x, y, and z dimensions. So x dimension is this, y dimension is this, and z dimension is this. The transformed j vector also has 3 dimensions. So what happened here is the two vectors I and j, which were in the xy 2D plane, it got an additional third dimension, and now you have a new plane in the 3D space. What do I mean by the plane in the 3D space? So what I mean by that is, using these 2 vectors, you cannot span the entire 3D space, because for spanning entire 3D space, you need 3 vectors that are linearly independent of each other. But these 2 vectors, they are linearly independent because the I vector and j vector, you can see that first of all, they are not multiples of each other or anything. They are not one scaled by a factor. So they are linearly independent, and these 2 vectors span some plane. 2 linearly independent vectors can span some plane. 2 linearly independent vectors in xy planes can span the entire xy plane. 2 linearly independent vectors in any other plane, any other 2D plane, can span that entire 2D plane. Now here, in this case, you are transforming a 2D space into a 3D space, which means the two new vectors, it might look like something like this. So this is the new transformed I vector and new transformed j vector. So this plane can be spanned by these two vectors. So what that means is, if the new transform vector is multiplied by a scalar alpha, and then you add that to the, so here I am denoting not by the cap because this is not necessarily a unit vector, and then the new transform j vector is multiplied by a scaling factor beta, you can do alpha I plus beta j, and this can be using a combination of alpha and beta. You can create any vector lying within this 2D plane, and this is the same 2D plane in which the vector I and vector j after transformation belongs to. But where is this 2D plane? Is this same as the xy 2D plane? No. This 2D plane, the vectors in this 2D plane will have one more additional dimension, the z dimension. So this is why we are saying the transformation is happening from 2D space to 3D space. But the amount of space that these two vectors can span is still limited to 2D. So that's what I have written here. A third dimension is added. You know where the I ends up, you know where the j ends up, and these two new vectors can transform the entire 2D plane in the 3D space. Now let's look at another example, which is the other case of a 3x2 matrix. So now we have a 2x3 matrix instead of a 3x2 matrix. So you have 2 rows, 3 columns. And again, here you know that each column corresponds to where the original unit vectors land. And since here are 3 columns, there are originally 3 unit vectors, which are I cap, j cap, and k cap. So the first column of this 2x3 matrix is where the I lands after transformation. So this we can denote as I transformed. The second column is j transformed. These are not unit vectors, so you cannot draw the cap, but you can maybe draw like a vector symbol like this. And the third column is where the k after transformation ends up. So what does this mean? You can also see that these three vectors have only 2 dimensions. It has only x and y dimension. So x dimension, y dimension for the the new I vector. So here I should not put the cap. I mean, this is where I lands, but this should be called as I transformed, something like that, right? So, but it does not have 3 dimensions. It has only 2 dimensions. But you know that the I, j, and k were originally like this: 1 0 0 0 1 0. So this was I cap, this was j cap, and this was k cap, and they have 3 dimensions. But after transformation, those 3 vectors only have 2 dimensions. So this is a transformation from 3D space into a 2D space. And here the interesting thing to note is the original 3 vectors I cap, j cap, and k cap could span the entire 3D space. But here, after transformation, these 3 vectors belong to the xy plane. And the third vector, one of the third vectors, can be represented as a linear combination of the other 2 vectors. So for example, here let's take 1 4 and 3 2 as the basis vector. So if we take 1 4 and 3 2 as the basis vectors, then the third vector is not linearly independent. It is dependent on the previous 2 vectors. So third vector is 2 2, right? We could represent this by solving an equation, 1 4 3 2. Let's say this can be represented using, so basically alpha times this plus beta times this is equal to this. So alpha plus 3 beta equal to 2, 4 alpha plus 2 beta equal to 2. So we can subtract this and we get 3 alpha plus beta equal to 0, right? Sorry, minus 3 alpha plus beta equal to 0. So 3 alpha equal to beta, that is 1. So alpha equal to beta by 3 basically. So we can now write alpha in terms of beta. So this is 3. Then beta by 3 plus 3 beta equal to 2. So 10 beta equal to 6, beta equal to 0.6. And alpha equal to beta by 3, which is 0.2. So I hope this gives the correct answer. Let me check So alpha plus, so alpha times 1 is 0.2 plus 3 times 0.6, 1.8. That is equal to 2. So you are getting 2. Then alpha is 0.2. 0.2 times 4 is 0.8 plus 1.2 equal to 2. So yes. So so basically the third vector 2, 2 can be represented as a linear combination of the first two vectors, where alpha equal to 0.2 and beta equal to 0.6. And you can do the same thing. You can represent this middle vector as a linear combination of the other two vectors. So these are not three linearly independent vectors. Yes, these are three vectors in which only a pair can be linearly independent. So what does this mean again? You are transforming from a 3D space into a 2D space, right? And in the 2D space, you have these three vectors. I have drawn the three vectors somewhere here. 1, 4, 3, 2, 2, 2. So 1, 4 is this. This is where the transformed version of I lands. Then you have 3, 2 and 2, 2. So this is 3, 2 and this is 2, 2. So this is J after transformation and this is K after transformation. But these three vectors span only the 2D XY space. So this is a transformation from 3D space into a 2D space. Now, that is exactly what is written here as well. The three vectors who could span the entire 3D space, after the transformation, they could only span the XY plane. Now here is another interesting example. Let's take a 2 by 1 matrix. So a 2 by 1 matrix means it has only one column, and this one column is the position of the vector, position of the original unit vector after transforming the space. So the original unit vector is in what dimension? The original unit vector is in one dimension, because the original unit vector, there is only one unit vector. So if a particular space has only one unit vector, it has only one dimension. So here the transformation is happening from a line into the XY plane. So here, let's say we take something like this. We take, so this 2 by 1 matrix can be multiplied by a 1 by 1 vector. So let's say 3 by 2, this 2 by, this matrix is multiplying with a vector like this. Then you have result as 9, 6. So did you see what's happening here? So here, originally the vector had only one dimension and the vector was like this. So 0, 1, 2, 3. So the vector that we were originally looking at in one dimension was along this line like this. And after transformation, what happened to this vector is this went to 9 over here and 6. So this vector got mapped into this. So this is this matrix, this 2 by 1 matrix 3, 2 is a linear transformation from one dimensional space into two dimensional space. But since you have only one vector here, this vector can only span a one dimension. And which is that one dimension? It is this line. The after transformation, you can only span along a straight line. Although the transformation is into 2D, you have only one vector, one basis vector, because in one dimension you had only one basis vector, which was the I vector. So this basically transforms the I vector into, so what is I vector? I vector in 1D is nothing but 1. So you are transforming the unit basis vector in one dimension into this coordinate 3, 2. So 3, 2 is here. This is 3 and this is 2. Right? So this is your basis vector after transformation. And in 2D, this basis vector can only span along that one single line. So although the transformation is increasing the dimensionality of the space, it is not enabling you to span the entire 2D space. So the span is not increasing. Span is still 1D. So that is the beauty of this 2 by 1 matrix. You are projecting from a line into a 2D plane, but you are spanning along a line in the 2D plane. Now what about 1 by 2 matrix? This is an interesting case. So here, because this is a 1 by 2 matrix, it has two columns. This is the first column, this is the second column. But you can see that each column has only one dimension. It does not have 2 or 3 dimensions. What this means is, you originally had two unit vectors, I and j, right? But they are getting transformed into two one-dimensional vectors. So what happens to, so let's say 1, 2, this is the transformation matrix, and this is 1 by 2, right? Now this can multiply with a 2 by 1 matrix, sorry, 2 by 1 vector that is represented by a 2 by 1 matrix. And let's say my vector is 3, 2. Then if you multiply this matrix with this vector, the transformation that results from this is 1 times 3 plus 2 times 2, which is 3 plus 4, 7. So this is just this is again like a vector, but after transformation, but it has only one dimension. So you are transforming this into this line represented by this. So this is 7, 1, 2, 3, 4, 5, 6, 7. So this is origin. So you are transforming this vector, which was originally in 2 dimensions. So it was 1, 2, 3, 1, 2, like this. It was in 2D, but after applying this transformation M, you transform this vector from 2D into 1D. This transformation from a lower dimensional space to higher dimensional space, or from a higher to lower dimensional space, is very commonly used in machine learning, especially in neural networks. So when you are multiplying with the weight matrix, the previous layer, you might be transforming the previous set of inputs from a lower to higher dimensional space, and sometimes back from higher dimensional space to lower dimensional space. So at the end of the day, the basic operations happening in neural network has very high significance to transformations using non-square matrices. So that is the importance of having a very basic intuitive understanding of what's happening in the case of non-square matrices. And although we talk in the language of rank, span, etc., the mental picture that you should have should be that of what is happening to vectors when this matrix is acting upon those vectors. And where are vectors present in machine learning? The input itself, input to a neural network, is in the form of a vector. And where are matrices in machine learning? You can have matrices representing certain kind of transformation as the weight matrix, and then this will linearly transform the vector into another space. And then you may perform some non-linear operations as well. We will learn that in the later part of the course, of course, but here I just wanted to show you a basic intuition of these non-square matrix transformations. This is very important and very common. So now this hopefully gives you a fairly good idea about linear transformations completely. In the next lecture, we will explore how to do inverse of matrices and what does it physically mean. So inverse calculations, we know we usually perform by calculating the determinant, and we can follow a certain set of steps. But what does it actually mean with respect to linear transformations? Is inverse also another transformation, or is it something else? In which cases inverse do not exist? What does it mean when determinant is 0? Why cannot we find the inverse of a matrix? These are some questions that can have very intuitive answers rather than just mathematical answers. So we'll explore those in the next lecture, and we will see how those things will help you when you finally learn machine learning. So thank you so much for listening this lecture, and stay with me, and you will learn about this intuitive understanding of some more fundamental concepts in linear algebra for machine learning in the upcoming lectures. So see you again next time. Take care until then. Bye.